This is my Physics 2211 Lab 2 Projectile Motion by Lachlan Poggins. So for the introduction, the purpose of this lab is to compare the position of a projectile affected by gravity and drag computationally and experimentally. We collected data from the Tracker app, and we also computed two models on GlowScript, one without drag or air resistance, and then one with drag. And overall, uh, we evaluated and analyzed the motion of a thrown paper ball um, while in lab. So now on to the physics models that we used in this lab. So the main principles were momentum and Newton's second law. Constant, constant acceleration equals 9.8 meters per second squared. And then force equals mass times acceleration. First, we have the final velocity formula, and then we go to the position update formula to predict the motion of the object, and then the force of gravity near the Earth, which is used and only affects the y component, and then we use the force of drag to show the component of air resistance and drag on the paper ball. So this is just an image from my Tracker app, and it has the motion of the ball, and I have about, I believe, 15 or so points while the ball is in motion. So for the system, we have the paper ball, which is a mass of 5 grams, and then surrounding forces of the ball, such as drag force. Here are both of the position versus time graphs that I got from the Tracker app. The top graph shows the x position, and it is increasing as time goes on, and then y starts at 1 meter and then goes all the way down to 0 over time, and it took about half of a second. Okay, so now on to my GlowScript code. As you can see on the left, we have the no drag, and then on the right with drag. So on the left represents the ball without drag, and you can see is the position updates as g is multiplied by t. And because there's no drag, that is going to be the only force acting on it. And then when we do have drag, we use the new FNet formula, which uses the drag formula, and to represent that, we use the ball velocity y squared, and then you can combine that with the force of gravity to find the object moving with drag. So now on to my computer versus experimental data shown in graphs. On the left, we have the observed position versus time graph, which I created in Excel using the data collected from the Tracker app. And next, on the right, these screenshots are pulled directly from the GlowScript code, and it is the trajectory of the object y position versus x position. So all models follow somewhat parabolic path with regards to projectiles for the projectile's trajectory. Additionally, all models show a slope equal to 0, and the maximum height of both computational models have the initial height as the max height. The trajectory of the no drag force reaches a greater horizontal displacement than the experimental observed trajectory and the computational model that has the drag force. This is likely because without drag, the only force acting on the paper ball is gravity, and with nothing opposing its motion in the horizontal direction, the paper ball uh, the paper ball in the no drag model will keep its full horizontal velocity until it reaches the ground. This allows it to travel further in the horizontal direction, which then increases the paper ball's displacement from when it was thrown. Okay, so some sources of error we could have came across were the use of the Tracker app. In Tracker, you have to manually click the center of the ball for each frame. It's possible some of my clicks were off from the center of the ball, which could cause some error. And another source of error could be the drag force we use is inaccurate. And lastly, and just making different model assumptions in the graph. So do the models predict terminal velocity? None of my models predicted terminal velocity since there is a net force in each model impacting the motion of the projectile. To find the terminal velocity of an object, you could perform a free fall experiment from a large height and track the object's velocity over time because the velocity will eventually level off and become constant. This is due to drag force. Drag force will increase until it balances the force of gravity, and then the net force will end up being 0. So what if the object was thrown straight up? If the object have had the same initial speed, the initial velocity would be entirely in the y direction. Thus, this object would reach a higher maximum height, so it would take a longer amount of time to reach the ground.